level equals 0, or if level is greater than 0, then we set them to here. Alright. Alright, and we need to make a level out of this. So we're going to say mlevels dot add let's just add in a level here. I don't want to copy everything all over the place. Alright, so we'll grab the level. Once we've shoved it into the array, we'll say the width equals width, and lev.height equals height. Do we need the total height? I think we need the total height. Alright, so int32 and total width, int32 total height. So we want the total width to be the width and total height to be the height, and then we want the left.in width to be the cur width, and lev.in height to be the cur height. Alright, so once we've actually made the level and we've initialized these variables, we need to make all the grid squares that are going to go into this thing. So we need to go for, like, you know, for every grid square and then write in a new tile for it. So we're going to say for what int32 x equals 0, x plus equals cur width plus x. X is less than cur width. Let's think about that. It's not cur width is going to be what, 512, and then it's going to be 256. So if it's going to start at 1, we're going to want to, x needs to be added to by the cur width itself. So x needs to be less than width, and it's going to be x plus equals cur width. And int32 y equals 0, y is less than height, y plus equals cur height. For every one of these, we're going to add in a tile to this level. So it'll be what? lev.mtiles.add. We'll just get a tile. So what'll that do? That will, if we were the first level, it's going to be 0, 0, 0 to start with. Alright, that's fine. We're going to want a void get tile for position, and we're going to pass in like int32x, int32y. We're going to pass in an int32 level, and then we're going to out tile will be something. So we need this function as well, which will help us later actually get tiles for a specific position and level. Alright, so we've added everything out here with this init function. All of our levels should exist, so we should be able to look it up. Let's comment after we're done here a little bit. Alright, so get tile for position. So for position and level. Alright, so we want to get it for a level. So in levels sub-level, let's see, level index, and so the actual level is going to be this, and so we're going to want the actual index in 32ax and AY. AX is going to be x divided by level dot in width. So this will be like, if we were 0, 0, the width would be 512. I guess it's going to be, we're going to divide by 2 times the level. X was x divided by 2 times the level index. And we could do shifting and all that crap, but it really doesn't matter. This is all static computation stuff, and the compiler will organize things as necessary if we really need it. It's all integer stuff. Alright, so y divided by 2 times level index. So let's take a look at this at level 1. If we were 256, 256, so let's just do 128, 128 on level 1. We're going to want to go into the top left square, so we should be getting a 0, 0. Now we should be dividing by the actual width, shouldn't we? Not the level. That would be the inverse of the level. So I think it's just going to be x divided by m width. So in this case, if we are in the first level, it should always be 0, because there's only one index. There's just, 0, 0. And then our tile that we're going to get, we're going to say out tile equals level dot m tiles sub ax plus this is going to be level dot m width, level dot height. So that should definitely get a tile for a specific position. Alright. Alright, so we write a pixel. We're going to go for what? In32 level equals 0. Level is less than and levels.num plus level, and we're going to say get tile for position. That's going to be pix.m.pos.x, pix.pos.y, level index is level, and out tile is going to be tiered average tile ref. Maybe we should do a pointer to a pointer, and we're just out tile equals what the address of this thing. So maybe that'll allow us to do it. So we just do the address of the tile here, and we do star tile equals the address of this. So that'll get this, and we'll just do tile mdir plus equals pix dot we don't have the actual position in this pixel, we have a direction that's written into the pos. So we need int32x and 32y. So we got right pixel, which is what we're actually doing right now. So int32x and 32y. The pixel. So d4 int32x equals 0. X is less than n map.inWidth plus x. 32y equals 0. Y is less than map.in height plus y. So calculated pixel pix equals pixels sub x plus in map.inWidth times y. xy pix. Alright, so we got xy. So it's going to be pix dot pos. And our magnitude is going to be plus equals what, pix dot mag. So that'll write all this in here for every level all the way up. Alright, so for getting our info, we're going to need our int32x and int32y. So get info is going to need to be oh man, I had some errors in here. These should have been references, not the other way around here. This is right pixel, not right. Okay, so references, pos 0, float mag, get info. Okay, so we'll get our info, and our info that we'll snag is going to be an out direction and out magnitude. We'll normalize it before we return. So what I'll also need here is I'll need a number of writes that I performed. And let's just go ahead and give ourselves a member initialization list here. Just kind of sneak that in there. Alright. So for writing our pixel, we'll write that tile m writes plus equals, well, just plus plus. And for getting our info, we're going to go through every level that we got. So we'll get a tile for our position on every level. So it'll be, we'll do outdir equals f vector 2d 0 vector and outmag equals 0. So what we're going to do is outdir plus equals tile dir, and should we multiply it by the level? No, let's just multiply it by, let's just say level plus 1. So it's just going to get like, you know, the weight will get stronger as we get more specific, and we'll just try that out. And we're going to want the number of writes, n32 writes equals 0. Alright, so we're going to want to know if tile m dir equals f vector 2d 0 vector, then we're going to continue. And this is not tile m dir, here it's tiles dereference pointer dir. Right, so we snag our info. We need to get the actual vector here, don't we? So I think we need to pre-calculate all these vectors. So we should do some sort of calculate, because right now all these vectors are not, we don't want to do for like every pixel do this operation. Let's just do, let's just call it post process. So we're going to post-process this data, which will take all the number of writes and everything and average it out for the level, for every tile in every level. Alright, so for every level, we're going to want to x equals 0 and 30, x is less than level, m levels sub level dot m width plus x, or m32y equals 0, y is less than m levels sub level dot m height plus y. We're going to want to say the tiered average tile t is in levels sub level dot in tiles sub x plus y times in levels sub level dot in width. So we're going to say if t.m rights is equal to 0, then t.m dir equals f vector 2d 0 vector, and t.m mag equals 0. Continue. Otherwise, t.m dir divide equal by t.m rights, t.m mag divide equal by t.m rights. And then we'll just normalize it. So that'll pre-calculate and normalize everything that's inside of our data structure. Alright, so we'll do our post-process all the values, then we'll fill in all of our averages. Which is this get info for this thing. So get info is xy fix outer mag. Fix outer mag. That's much better. Holder get info should do that. And 32x and 32y. Okay, so we post-processed it. The get info should add all this together. Alright, so the number of writes is not actually going to be 1. It's going to be writes plus equals level plus 1. So because we're going to write, like, if this is an average, we're basically adding, like twice the second level and 3 times the third level. So if we're going to get a true average, we're going to have to multiply the number of writes. And at the end, we just do out dir divide equal by writes, out mag divide equal by writes, out dir dot normalize. Alright, so out mag plus equals tile and mag times level plus 1. Alright, let's see if this compiles. Because I think we've got our data structure written out. So what is this complaining about? This is complaining about not having a body for that function. Well, that's simple enough. So pretty simple. And we'll clean up the code once we kind of get it working how we want. I'll throw function headers and I'll just like bury this at the bottom of the file where nobody will ever look. That's how all your data structure code should be. Dead and buried. Are we actually calling all this garbage that we just wrote? So we have this right tiered average. We are actually calling it. So we'll see if this actually does anything, or if it's just a whole bunch of garbage. So this should fill in all the blank areas in our entire map with a tiered weighted average of the things that were around it, and I have no idea what that's going to look like, but it should fill everything in. So we'll tick all this stuff, and then we'll do generate flow field. Yeah, the ticking is the big expensive one because it's actually running like all these particle simulators here, which is kind of an expensive operation because there's a lot of calculations that go into it. Like, there's momentum for the particles, they have to decide where to go, and like all this other garbage. And there's a lot of particles. Alright, and let's generate the flow field. And we crashed because level, total width and height is 64, level 4. There are 64 tiles. So x is y, x is 0, y is 64. Well, get tile for position. There are only 64 tiles in here with a width and height of 64. Alright, so the y is going to be 64. The level m height is 64. Let's not think, let's actually do this. So it's going to be 64 divided by 64, which is going to be 1. So we're using level m width, which is 64, so it's going to be 64 times 1. If this thing has only 64 tiles, like this thing should not have 64 tiles, it should be 64 times 64 tiles. So this initialize didn't actually give us the right number of tiles. If we're level 4, so that's going to be 0, 1, 2, 3, 4. So we should be 64 thing. It's going to be that these tiles were not added properly in the beginning, because this calculation appears to be correct. So what's wrong with this calculation here? We're going from 0 to 64, And 0 to 64. Well, we'll try it all over again. Alright, so curve width is 85. Width divided by 2 times level. So 512 divided by 6. Yeah, it shouldn't be 2 times level, it should be 2 to the power of level. And that's not a C++ thing, is it? We can't just use the hat. Should we just do shifting? Oh, you can actually just use the hat. That's pretty cool. I was unaware of said hat abilities. When did that get added? Okay, the hat operator is a bitwise, or it does not work for raising to a power. Alright. So yeah, there's a reason I'm like, that's not the right syntax, is it? Alright, so what we should just do is, we should just say curve width equals width shifted by level. Let's just do the shifting because we can. I don't like doing shifts and other things like that. One of the big coding philosophies that I follow is don't be clever. And I think anything that's basically beyond literally just like plain English pretty much is being clever. So even if it's like, well, we could divide by, 2 to the power or whatever for this integer and like, save some instructions or something, it's like I really just don't care unless there's a real reason for it in terms of performance. But when shifting is like for reals, like, if you have network code or something, you're packing bits into the header for something, and you're like, well, that's a place where you expect complicated, stupid crap to happen. So, doing clever stuff there is just fine because you don't expect that sort of code to be dead simple. You expect it to be like, all right, we're going to pack some stuff in here. I got to be real careful about this. Versus if you got like, you know, like some code to make somebody jump, you're just like, well, why isn't this just like character.jump? And if it's not, then there's like character dot, you know, move in up vector or something with velocity. You're like, well, why isn't there just a jump function? This seems like overcomplicated. So we calculate this, generate the flow field. Let's make sure we don't crash this time. So curve width and curve height. 512, 512, 256, 256, 128, 64, 32, 16, 8. Max levels is 64. So what? This will be 0, 1, 2, 3, 4, 5, 6, 7, 8. So we want to shift 1, 2, 3, 4, I believe. That should do it. So we're gonna take a couple levels. We don't need like pixel perfect stuff. So if we shift 4, it's going to shift from 2, 4, 8, 16. So it's gonna be, we're gonna minimum 32 by 32 grid squares, which should be fine. Alright, well, we are on the last step of all this water shenaniganry in terms of gathering information. Once we get this flow field in here, we'll actually be able to make water. What a concept. You know, we'd actually be able to get to what we've been trying to get to for weeks. Alright, so this thing is hung up somewhere. And the question is it because it is hung up, or because we wrote an infinite loop, or is it hung up because it's just going to take a little while to calculate all this? Well, supposedly it's running at like 50% power here. Let's go ahead and pause it and see where it is. We're calling init over and over again. Curve height is 0. Max levels is 32. So we're supposed to take the square root? No, it's Let's see, what we're going to want to do is see how many times we have to shift this thing to 0 or whatever, and we just want to subtract something from that. Is there an easy way to do that? I haven't done a whole lot of shifting crap for quite a while. I mean, it's basically what the log base 2 of the thing, but I guess there's probably an easier way to do this. Let's just hard code it for now. I should probably know how to actually do that, but I don't know. I'm a server engineer, not a graphics engineer. Screwing around with powers of 2 and stuff like that just is not something I ever had to worry about when writing calls to a database. A lot more of that is graphics and all that. So calculate this back out, and we'll see what it is. Maybe we'll get to something actually interesting. But today is not that day. Alright, so our X and Y, the tiles are wrong again. Width and height is 64 by 64, but somehow we only added 64. We didn't actually add the correct anything. Why? Like, it should be 64 by 64 in terms of tiles. So x equals 0, x is less than width. Is it cur width? It's supposed to be x is less than width. Doesn't matter. Really doesn't. Doesn't matter. Let's just ignore everything and stop trying to be clever. Let's just say if you're 64 by 64, then make yourself 64 by 64. That's really not a problem. So love dot in tiles dot init cur width times cur height. So just get rid of that stupid loop and just initialize our vector out properly, our array out properly. Alright, take a look at this. So yeah, we just gotta sit here while I calculate all this stuff out. I could probably have less ticks and all that stuff. And this would go a little bit faster, but whatever. Then I'd have to like do more coding instead of just sitting here staring at a screen. And that takes work. You know, like, who wants to do that? Alright, so this is our grid for everything, so let's think about this. What direction is everything in? This is kind of what I was worried about, is that we would actually see the grid on here. Alright, so this is like, well, this is interesting. These pixels here that are the shore pixels are actually contributing quite a bit to this. And we really don't want them to. Well, let's put in some other rules then. So let's not have all these things weight so heavily. We could have another tier, and that would lower the size. I think we'll do another tier. So this is 0, 1, 2, 3, 4, 5. So this will be the 16s. Alright, so we'll write these things, and when we call get info, let's just do writes plus plus. do it that way, so we won't scale this out. And let's think for a minute here. Do we want to write the shore values in here? We might not want to write the shore values. Or we might want to write multiple shore values. So it would be like if pix dot, yeah, pix dot particle. No, this could turn into some sort of problem. Let's just try not writing them. So alright, so why don't we just say if this is a zero vector, or if right, it does not equal zero vector, and the path is I guess we want or. So if the position is zero vector, so if it's a zero vector or these ANDed together, then we continue. I usually find it easier to kind of write logic for breaking out of loops, like, well, if this is a zero vector, or if it's not a particle or not a path, then don't do it. As opposed to sometimes an affirmative conditional. It can be more complex because you're actually most of the time throwing stuff out in conditions. Like, if it's this, then don't do this. I don't know. So we just got to play around with this and see what we get. But I was trying to avoid that grid effect, and I was, I guess, unsuccessful in the first stab here. Should be too heavy a weight towards the local values, so we'll try otherwise. So red is this direction. Yeah, that's looking better. That's looking a lot better. Because, I don't know if you can see it as well as I can, but there are multiple different grids that are being affected here, so it's not like we're seeing only one size of square. And that's what I'm looking for, is these grid squares actually coming together nicely. Not just always being present, but being like, well, these averaged out properly and everything. So that's looking alright. Hello, Synachron. I'm just working on filling out the intermediate blank pixels with the proper stuff. And that is looking alright. Hopefully this thing does what you want. Yes, that is usually the hope. So I think we've got this thing nailed down. Why don't we think about this a little bit? So green is kind of bottom right. Green is more top right. So these things are all flowing like this direction and this direction. This is going. So something flowing here would go over here, be repulsed, and then keep going around. This something coming here would be repulsed out and be pushed up, and then would kind of travel along that way. Something here would be rebuffed here and kind of come out. Yeah. We need all that complex math. And how we did this is we didn't add any of the shore stuff, we just used only the particles to create this tiered thing, which appears to have worked pretty well. Alright, so we need a rough blur pass where we blur all pixels with surrounding pixels except skip things set by particles or paths. So that'll blur like all this garbage except for the pixels, and then we do a fine blur pass where we blur absolutely everything. Alright, so we're getting there. Shitty numbers. Yeah, shit. Well, I'm gonna be right back. I need to go refill my water bottle.